let's do that. All right. Well, thanks very much for the organizers for yeah, having me speak. I know that Frank has really helped me a lot in my career. I'm going to wait until I'm no longer nervous at the end of my talk to tell an anecdote, but I am very appreciative and very glad to be here. So when I was trying to decide on what to talk about, I eventually landed on this topic, so mixed volumes of chemical reaction networks, and because it ties together a lot of the themes of Frank's work. So especially the topic of chemical reaction networks, right? We have numerical algebraic geometry comes up, enumerative problems come up, and sort of also, what was the other thing? Oh, real solutions, exactly, yeah. Real solutions to parameterized systems of polynomials, right? All of Frank's favorite topics sort of appear. It was also probably the one thing that the one sort of topic that I've had the most interaction with Frank with. So this is a picture of Frank, and he's sort of, residing in the archetype of educator here, teaching us about the global attractor conjecture in San Jose. This was a workshop organized by Nikki Meshkep, Bernd, and Matthew Johnston. All right. So what is a chemical reaction network? So chemical reaction networks are sort of defined abstractly by a triple. And so you start with a collection of species. And so in this case, in the example that I have, my species are A, B, and C. But you can think about these as molecules, or if you're thinking about ecological models, they're actual species, or if you're thinking about epidemiology, they're compartments. And then you have a directed graph. And so the vertices of the directed graphs are linear combinations of these species, and we call those complexes. And then you have edges between the complexes, and this is going to tell you how things react. So a reaction network in itself is just a graph, and then you need to put some sort of kinetics on it if you want it to model something, or model something over time. So one of the kinetics that, especially in the applied algebraic geometry world, that we like is mass action kinetics. And so one of the reasons we like mass action kinetics is because it's going to give us a system of polynomial ODEs. So mass action kinetics tells us that the rate of reaction is proportional to the product of the concentrations of the species. So in this particular example, okay, it is a little bit weird. Okay. So in this particular example, I'm going to denote the concentration of each of the species by XA, XB, XC. And then there's a recipe, right, to go from this network down to this polynomial ODE. And so in particular, you're just going to go through each of the species and you're going to see how they change, and that's going to tell you the coefficient. And so we can sort of just work through maybe this first one. So if I'm looking at how A changes as I go along that reaction, I lose 2A, all right? And so I'm going to get this -2 right here. This is like really hard, like I'm pointing over. Oh, maybe it's because you're pointing over there?
I think if you let go of it and then point it at where the cursor was on the screen before you hit the button, it might be easier.
Okay.
Then you'll advance the cursor.
Oh, yeah, all right. Okay, weird, all right. Ooh, okay, whatever. All right. So, and I want to look at that rate of reaction. Well, the rate of the reaction is proportional to the product of the concentration of the species. So if I look over at there we go, at what is over on this side of the arrow, I have 2 A's, and so that's going to correspond to a monomial, and in this case, that monomial is going to be XA squared, all right? And then I'm going to have this rate of proportionality, which is this kappa 1, which is also what is labeled by on that edge, all right? So the main thing is, we have a network that looks like this, all right? And then I write down this polynomial ODE, all right? The assumption of mass action kinetics sort of makes it polynomial and makes us understand these monomials really well because they are associated to the vertices of this graph, right? So each of the monomials that show up here correspond to a reactant over there. All right, so what are these used to model? So a couple of things. One, canonical example is the SIR model, which we've seen quite a bit. Other models, I'm going to talk about signaling pathways in a second. Another example is from ecology. So here's a very nice picture. This is actually taken of a coral reef 230 meters down. in a channel off of Maui, all right? And so basically the ecologists have recently been also using these reaction networks to sort of model things like endosymbiosis. Their chemical reactions are pretty straightforward. So we're just gonna, take a real quick look at what their reactions look like. But in particular, this particular paper is looking at endosymbiosis between coral reefs and algae. So you have, especially in marine biologists, you'll have sort of these, what happens is the algae sort of takes up residence in sort of that gastric cavity of the coral. And then there's this symbiotic relationship, basically. The algae feeds off of the coral, and then the algae creates energy and nutrients for the coral itself. And so it has this ecological advantage, right, for both of the species. And in fact, in some cases, sometimes this algae can create like 95% of the energy needs of the coral, all right? So it's actually, and especially as we care more about how we protect our coral reefs, understanding this process is more important. So in this particular paper, when they were looking at it, there were 3 different types of reaction networks that they had going on. One was just on the organisms. And so this is just sort of seeing, you have a predator. The S represents the algae or the symbiont, the S represents the algae, the C is the coral. And then it's just looking at the presence of a predator and how that's going to affect whether or not I have the algae there or not. And then you can also look at it in the intracellular and intercellular level. So in fact, you're going to have some things happen at both the cells sort of interacting on the outside of each other, and then one of the cells is actually going to sit inside the cell of the other, and you have some other reactions taking place. All right, so that's one application. Another application, which is the one that sort of comes up, especially in these chemical reaction networks that you see in this applied algebraic geometry world, especially like with work of Ann Shu and Alicia Dickenstein, has to deal with signaling pathways. So in signaling pathways, I have a cell, and my cell needs to make a decision. It's going to, when it wants to sense its external environment, and a signal is going to be sent through down to the nucleus, something's going to happen, and that signal is going to be sent back out. And how are these signals sort of, go all the way through? Well, it's through a series of molecular interactions, all right? So some of these popular molecular interactions might be something like phosphorylation, which adds a phosphate, etc. All right? And so here's an example of one sort of type of signaling pathway. So people really want to understand this Wnt pathway because it's associated to certain cancers and certain neurodegenerative diseases. And so what will happen is, you have it in the Wnt on state, right? What will happen is you're going to have a signal being sent down, and what's going to happen is you're going to have too much beta-catenin. It's not going to be regulated. It accumulates. And then what happens is it gets sent, the signal gets sent to the nucleus, and you have cell proliferation, which is not necessarily what you want in sort of cancers. All right. In another state, you're going to have some degradation, which is going to be a more desirable sort of outcome. So that's sort of what a signaling pathway looks like. And so then you can model these, right, using these reaction networks. So here's a particular model for this Wnt signaling pathway. This is appeared in this paper by McLean, Spi Rosen, Helen Byrne, and Heather Harrington. The network is over here on the left, and on the right we have that ODE that we can read off like a recipe. In this particular example, right, the first example I had and just had 3 species and a couple of reactions. And now I have, in this particular case, I have 31 reactions and I have 19 species. So my polynomial system is growing, and we need sort of tools to handle this. All right. Along with these ODEs, what I get is I also get a collection of these linear equations that we call conservation equations, okay? So basically all the dynamics are happening in a fine space. This is sort of telling you that space where the dynamics are happening. So without those equations, I would get like a 5-dimensional variety, and then this will cut it down to 0-dimensional. All right, so if we look at this, this particular model, we can analyze it. We can see, we can ask our favorite questions, right? How many solutions does this system have for generic parameters, right? That's one of our favorite questions that we've seen over and over again. Hold on, all right, throughout the last few days. Okay, for this particular one, we're going to get 9 solutions. We can ask how many of them are going to be positive. So actually, we can find parameters where 9 are going to be positive. We can ask how many are real and positive, right? And the most I think that anyone's been able to find are 3. I don't know if anyone's been able to find more, but that's the limit. All right. So we can ask all of these questions. We want to know, why do we care about those numbers, even if we're dealing with like generic complex parameters? Is it because there's some hope that it can give us some clue into what we really want to know, which is the number of positive real solutions, because that gives us a hint about multi-stationarity. So what can happen is, right, I have this ODE, and I can have, one stable steady state, right, and that would be monostationary, all right, or I could have multiple, right, and I want to know whether or not my network has the capacity for multiple steady states, right? And why do I want to know this? Because this is going to help me with model selection. Because if I am observing a physical process where if I change certain things and I'm seeing two different steady states occur, I don't want to model it with something that doesn't have the capacity for multi-stationarity. So it's a crude way to do model selection. So in particular, in this Wnt shuttle model, it has the capacity for multi-stationarity, right? And so since I'm seeing that behavior, that's sort of one of the things that makes it a good model. All right. So how do I get a handle on this? I mean, using the tools of the themes that have come up in the last few days, especially in Matthew's talk, right? We just saw the mixed volume as a way to bound the number of solutions. And I think in Matthew's talk, we even saw the Minkowski sum coming up. All right, so we're going to first, we're going to try and bound this with the mixed volume. And the other reason why we like this class of equations, right? So they have this very compelling application, right? And I'm talking about understanding cancer, right? This is very compelling. But they're also a very nice sandbox of equations, right? Because I have this combinatorial structure that's telling me about a polynomial system, right? It gives me a set of things to play with. So if I want to ask about mixed volume, this gives me a family of systems to look at that are actually sort of coming from applications. And so we want to look at this mixed volume problem for chemical reaction networks, all right? And so I think we've seen, how we, a little bit about the mixed volume so far. So I need, each of my polynomials. I'm going to have a Newton polytope. To get that, I sort of plot all of my exponent vectors there and take the convex whole. And then I'm going to take the Minkowski sum of all of the polynomials that appear. And then if I write maybe the volume like this, right, and I look at the coefficient of this term of the lambda 1 to lambda n, then that's going to be my mixed volume. And I have a couple of different ways to define that. I'm just going to define it in this way for this talk. All right, so what we can think about, the canonical picture, I think even Matthew had a little bit of a similar picture in his talk of a square and a triangle, right? So I take the Minkowski sum of the square and the triangle. This is going to be the Minkowski sum. I look at the volumes of these mixed cells, and the volumes of those mixed cells is my mixed volume, all right? In the two-dimensional case, it's very easy to compute because you just sort of subtract off your original areas, all right? And so we have this BKK bound, which tells us that the number of solutions, right, in the algebraic torus is bounded by this mixed volume, all right? And so now we can ask the question of, what are mixed volumes of chemical reaction networks? How do the combinatorics guide the mixed volume, and sort of look at questions like that. and that didn't work. Oh, that one didn't display, but that's okay. That's fine. All right. So we'll go here. So the other slide just had a bunch of like all the papers that were known on mixed volumes of chemical reaction networks. So I'm just going to tell you what they are and what some of the interesting things. So these haven't been studied that much. So there's like a handful of papers. I'll talk about a couple of them, but a couple of interesting ones that I also wanted to pinpoint. One is this paper with Nita Obataki and Shu, and I can forget her name, her first name, but Sophia. And they look at, like, they do a systematic study of the mixed volume. They basically look at, there's 210 reaction networks with 2 species that are at most bimolecular and with 2 reactions. And all of these networks, they have at most one solution. And so then they look at the possible overcounts. So in all of the cases, except for these 16 cases, right, that they got that the mixed volume was exactly the number of solutions. And so these are the 16 remaining from those 210 where you actually have an overcount. So I think that this is sort of an interesting paper in that regard because it gives us a place to start. And then some other work by Ann Shu, Nita Obataki, Angelica Torres, and Xiaosheng Teng. They looked at this 3 versions of an ERK network, and they used the mixed volume there. And there they actually used the mixed volume to say something about hop bifurcations. And that was also a very compelling piece of work. I think, I'm going to talk about a couple of families of networks that we know the mixed volume on. And I would say where, some other work that takes it further, and also that I really wanted to give a shout out to, there's also another piece of work by Nita Obataki and Elise Walker on the Newton-Akovenkoff bodies, right, and using that to bound the number of solutions. And there they actually, in that paper, they look at this, that Wnt shuttle model, and if I just compute the mixed volume, I think it's like 56, but if I use this, this no-body, and the no-body, I think is Frank's term, or no? Whose term is this?
Oh, it's old.
It's old term.
As soon as people discovered the acronym.
All right.
After watching the paper.
Okay.
Paper, they start calling it nobody. Dave Anderson calls it nobody.
Dave Anderson calls it nobody, but I love this term, right? So if I use, yeah. Yes, exactly. So in these particular networks, you can have like no solutions or one solution. Oh yeah, sorry, no positive solutions. Yes, thank you. You can either have no positive solutions or one real positive solution. All right. So in that paper, in that no body paper, they were actually able to almost cut this like bound in half in there. And I think that might be like a new direction. You'll see like, in a couple of the examples, some of these mixed volume bounds are sort of arbitrarily bad. Maybe we need different tools to look at it. And then I think the other thing that's sort of compelling that people have been talking about, and it came up like very quickly, I think in John's talk, was maybe like vertically, I don't know if your system was vertically parameterized, but like people have been, like UA-REN has been looking at these vertically parameterized systems and using some tropical geometry there.
Yeah, the next talk is going to address that.
Oh, okay, great. All right. But these are fun families because they fit into there. All right, oh, and none of my pictures are showing up. That's okay. Oh, yeah. Okay. All right, that's fine. All right. Something's done. I don't know if it was when I uploaded it or if it doesn't like Adobe. Okay. What? All right. Whatever we're going to imagine. All right. So let's look at, so what I want to do now is, so this first paper was with Svetlana Hill, and we looked at 3 families of reaction networks and looked at the mixed volume for each of these 3 families. And I like the story from this paper because it's sort of like, we'll see, it sort of really starts in this very simple sort of setup, and then it gets more and more complicated. And so it's a nice story to sort of tell in the talk. All right, so the first one looks at this model of apoptosis or cell death. There you have a picture of what the model is, but you can just imagine a reaction network. I think the main thing that you need to know here, oh, and I'm not gonna have the arrows. Maybe I'll grab my computer to get the arrows right. Right. Because you guys do need to know what the network's gonna look like. And I'll get the arrows wrong. It's fine, I'm not gonna hook up, I just want a cheat sheet. All right, so these actually have very particular sort of structures. I think I'm gonna have like 2y, 2z, z plus y. The arrows are unidirectional. I forget which ways they go. I think that these ones go this way, and I forgot which way that goes. And then they're just complete graphs, okay? And they're gonna have two species. So I'm just looking at all of my ways. I'm going to take two variables, z and y, and then I'm just looking at all of the different ways that I can, sum to 3 in this case, right? And I get these complete graphs. Again, the arrows go some way, all right? I'm sure we can actually figure out which way the arrows go from the equations. All right, but this is a very simple model, and it's sort of interesting, the things that I want you guys to pull out is, number one, is that they're complete graphs. Number two, they're gonna be a family of models where they only have two species. So this means that I'm fixing the number of variables to be 2, but I'm growing my network, okay? And so these are the reactions, and actually here, you guys can sort of fill in my arrows. That's like a task for the audience, yeah. You know what? Actually, I don't know, but I can look that up for you and let you know. All right, but you guys can fill. I have something that doesn't have directions there. Now you can just sort of fill it in, sort of like fill in your own notes, sort of thing. All right. What was that? It goes towards more Z's. All right. What was that?
The Z's are dead.
All right. So it goes towards more Z's. Thank you, Taylor. Awesome. All right, so then I can do the same thing where I read off the equations, and then I get one conservation equation, which is going to be something where it's just xy plus xz minus c1. All right, and so we can, compute the mixed volume, and notice, right, my number of variables is increasing, and so my mixed volume is actually going to be, in terms of this number of variables, and so it's going to be n minus 2. And actually my steady state degree, so my number of solutions with generic complex coefficients, including boundary steady states, is going to be n. So here I fix the number of variables, but my mixed volume and my steady state degree is growing. And so we can look, this is, a fun one to do mixed volume on, because I just have, all of my steady state equations, right, are going to give me stuff that lie along this line, all right? And, oops. And so I want to really take the Minkowski sum of this with this, and so, this is, our high school geometry, maybe even like middle school geometry, right? And I get this trapezoid. And so it's easy for us to then figure out what the mixed volume is, and I get to write out, okay, this was that esoteric sort of definition that I had on the previous page, but now you can see what this coefficient looks like. And in the two-dimensional case, right, I can literally just solve for it. I want to sort of subtract off the triangle and I'm going to subtract off 0 because this is, 1 dimension less. All right, so that's our like simplest sort of case, all right, coming from this cell death. But then we can sort of look at sort of more complicated examples. So here's an example that's coming from chemistry. And so we have this Edelstein model, which it has 3 species, all right, and a sequence of reactions there. And then we can create like a family. So E2, I'm going to do sort of the same thing, but I'm going to be adding in a B2. At E3, I add in a B3, etc. And so now my number of variables is actually increasing, but my mixed volume is going to stay the same in this particular case, and my steady state degree is also fixed. And this is an example of a multi-stationary network that exhibits multi-stationarity. All right, and then this one, we use a couple, some more complicated machinery. So there's this nice theorem that I believe appears in a paper by Rojas in 1994, and then again in a paper by Tianren Chen in 2017. And so here, what we can do is if R, I'm going to have a series, all right? So these are going to be my equations, all right? I'm going to get 3 equations here. And I'm just sort of looking in this first case. And I can think about as S1, S2, S3 are going to be my exponent of vectors for each of those polynomials that I have there. And then this condition says, okay, well, throw everything into one set here, and then check each of these conditions, all right? And so I'm going to go through each of the faces that I get from this convex hull of S tilde, which is everything. So this is going to be this picture here. This is the convex hull of S tilde. And then I'm going to check. I'm going to say, okay, does, one of 2 things needs to happen. My face needs to intersect each of these SI's, all right, for all of the I's, or my face is going to intersect one of the SI's as a singleton. So, especially if I am a vertex, that's going to happen. All right, and so we can actually check this. So if I look at this face right here, it's a little bit small for you guys, but it's 0, 0, 2, 2, 0, 0, 1, 1, 0. And I can just check that I actually, intersect each of these, right? So for S1, I'm going to intersect at the 2, 0, 0. For S2, I'm going to intersect at the 0, 0, 1, and same with S3. And so, in fact, for this family of Edelstein networks, this always happens. And so then we can use this to actually compute the mixed volume. All right. And I want to go, all right. So we can use this to compute the mixed volume by just computing, basically, the volume of that convex hull. All right, so one more where my picture doesn't show up. Now I'm like curious. Oh, okay. All right, so then the last one that we did with this paper with Svetlana Hill was we looked at this multi-site phosphorylation. So like I said, when I'm modeling, maybe signaling pathways, a lot of the signals are being sent forward through a bunch of molecular interactions. One of these like sort of fundamental molecular interactions is this phosphorylation reaction. And maybe this is where I now draw what this looks like. So you guys have a picture, and it's not so. Oh, thank you, but I don't know that. All right, so I have S naught plus E to X to E plus S1, and then S1 plus F. So I have some substrates here. And I think that is S0. All right, so this is like, and this is, I'm using the notation that they tend to use for this phosphorylation network. All right, the S's sort of are standing for substrates. So as again, this very sort of simple network, this is the one-site phosphorylation. You can either have a distributive process or a processive process, all right? we're going to look at the distributive, which is the one that I have there. And this system has actually been studied quite a bit. So just also in terms of real positive solutions. So there's been papers that have looked at the regions of multistationarity. Wang and Sontag have this 2008 paper that bound the number of real positive solutions to this system. So this is a single site, but I can imagine going up to n site, and my system gets more and more complicated with more and more variables, but it has the same structure as I go to more sites. And so the Wang-Sontag result tells us that the number of real positive solutions is bounded above by 2n minus 1. And there was a later paper where it said that this bound could actually be achieved. All right. And in fact, I believe that I'm saying this as a conjecture because it's not specifically written, but this is sort of hidden in that Wang-Sontag paper, I believe, that the steady state degree is going to be 2n plus 1. So you're only sort of off by 2. All right. But when we compute the mixed volume, so this is linear, right, in n, when we compute the mixed volume, we get something that's quadratic in n. And then this one was, again, at each step, we're getting more and more complicated. So this one, we end up having to compute the normalized volume of a 3n plus 3 dimensional 0, 1 polytope. It has 5n plus 4 vertices and 3n plus 7 facets. Spetalina Hill sort of basically really worked through constructing a unimodular triangulation for this polytope. So there were a couple of things that needed to take place, right? We needed a facet description, which is not always super simple for a polytope. And then we went through and did vertex placing to get a unimodular triangulation, and then you count simplices. And so it was sort of, it was a very interesting sort of combinatorial adventure, right? And then one of the cool facts is this polytope that we needed to compute the volume of is actually a matching polytope. And so this is the graph over here. And so the polytope would be the matching polytope of this graph. All right. So those are three, I can sort of summarize those three examples and sort of see the different behavior that we're getting. So, in the cluster model for cell death, I'm getting that basically the mixed volume and the steady state degree are both sort of linear, or in this n, which is really my sequence of families, not necessarily my variables. All right, we can actually show that we always get like exactly 2 boundary solutions, and so that's where the 2 is coming from. The Edelstein, we have sharp between the steady state degree and the mixed volume, and in this multi-site phosphorylation, we have a quadratic for the mixed volume and linear for the steady state degree. So then, we wanted to look, like I said, there's like literally like no papers. I mean, now there's papers. Now there's like 5 papers. But when we started this, there was like no papers on mixed volumes of chemical reaction networks. And so it was a very sort of interesting sort of problem and a family to explore. And so then for the next project, so now I'm going to change gears, and this is a project with Jane Coons and Mace Curiel. And we wanted to, look at mixed volumes, and we wanted to look at mixed volumes for binomial reaction networks, okay? So let me explain what a binomial reaction network, so I can create an ideal, with my steady state equations, which are my ODEs here, all right? And if this ideal is generated by binomials, I'm going to say it's binomial. And these have been studied in the sort of the chemical reaction network literature. So there's a paper by Perez, Dickenstein, Shu, and Conradi, and they define these toric steady states. So they say a chemical reaction network has toric steady states if the ideal is binomial and it emits a real solution, all right? So if it doesn't, I'm going to use the language of binomial if it's generated by binomial, and again, toric steady states if it actually emits a real positive solution. So, yeah.
So does generated by binomials more or less mean like every
it doesn't.
if you're sometimes in the system and
it means that like at the, I can find generators that have like one part and two, that are just like a sum of two things.
Right, sure, but
Oh, okay. Oh, does it imply?
list of reactions,
Wait, I'm gonna repeat that.
in terms of the list of reactions, does that amount to saying that each reaction appears 2 times?
This is an interesting question. I'm not sure. We can sort of work it out. I don't think you would, because you could have like I don't think that this is necessarily the case. Okay. All right, so if it's generated by binomials, I'm going to call it binomial. So why were we interested in these? Well, so me and Jane and Maze also come from algebraic statistics. So in algebraic statistics, right, we look at very similar things. So number one, in Sonia's talk, log linear models came up. Log linear models are generated by binomials. And in Jose's talk, the maximum likelihood degree came up. And so if you actually care about, if you want to compute the maximum likelihood degree for log linear models, you have to sort of compute a system that looks like a sequence of binomials and some linear equations, all right?
Yeah, let me maybe rephrase the previous question. Can this be detected from the reaction network?
Oh, yes. All right, and actually I'll have that. I have a condition that they give on the next slide. It's actually, let's talk about, I'll show you what it looks like, and then you're going to see whether that answers your question or not, and it probably does not. So there's no like nice combinatorial way to detect it from the reaction network, okay?
Do you want the idea to be prime?
No. For mixed volume, we do, and I'll talk about that for a second. Like I want a complete intersection. All right, I'm going to talk about that. I need squareness. But in general, for this, no, it doesn't need to be prime.
Well, don't you want to parameterize the steady state? So
Yeah. Well, yeah, but so the ones that they look at here are not necessarily prime. Like a lot of the ones that come up in like real settings are not necessarily prime. They're binomial, but they're going to have like one torque sort of component, and then that torque sort of component is the one that you parameterize. Yeah. And the reason why is because you have like some boundary sort of components. After you saturate out, usually by the boundary components, then you end up being prime. All right, so here's a question on whether or not it can be detected. So I just wanted to sort of give this, so this was a condition due to Perez, Dickenstein, Shu, and Conradi. And so they do give one condition on how to detect something was binomial, all right? But you can see that it's a little bit, in some ways it's sort of nice. It's just a linear algebra condition. So you're looking at this complex to species rate matrix, and you can just think about that as the matrix that's sort of, if I just rewrite my polynomial system, you can think about that as the matrix that I would get. And then I'm looking at the kernel of that matrix and the dimension of that kernel. And then I'm looking on whether, a basis of that kernel, and I'm seeing if that basis of that kernel has sort of disjoint support, and I get everything. So yes, you can detect it from the network, but it's like not so easy. Yeah. And I think like some of the conditions on how you detect it from the network are actually quite interesting. I think that there's more room to sort of ask these questions and really explore. And we were, how we sort of started on this project too, was we were really interested about this condition and seeing what networks sort of satisfied these conditions. And so this is not an if and only if either, right? This is just sort of giving you, like a sufficient condition for binomial, right? But I also wanted to put this up there because it has this theme of disjoint support, which we're going to see come up in a second. All right, so one class of networks that actually satisfies this are going to be these species overlapping networks. So in fact, we can look at, we started just to look at cycle networks to see if we could tell if they were binomial. And so my student, Maze Curiel, is actually really good at combinatorics, and so he has a nice if and only if condition on just any cycle network, whether it satisfies that condition on the previous slide based off of a coloring condition on these vertices. So that's a very combinatorial thing that you can check from the network, all right? Here is sort of some cycle networks I want us to be our focus for the next couple of minutes. And these are going to be species overlapping networks. And they're pretty straightforward. And in fact, these steady state equations are already going to come to us as binomials. So we don't need to use that condition to check if it's binomial, but it does satisfy. There's a family that satisfy those conditions. All right. And they're highly structured, right? They're at most bimolecular, and they, have this overlapping pattern here. Okay. So, I have a B here, I'm going to have a B here, C, C, etc. And there's going to be a difference. There's going to be a difference between this odd cycle and this even cycle. So now we want to compute the mixed volumes of these. In order to compute the mixed volumes, we do want a square system. And so in this particular case, for these networks, these last, actually I have a slide, okay. So the gray equations are not necessary, so I can get rid of them, and I will always get a square system. I'm just sort of replacing the conservation equations with the last few equations. So in one of the cases, I'm replacing 1, and in the other class, I'm replacing 2. Okay. And the other interesting thing about these networks is if I look at these conservation equations, right, they're going to tell me something. They're like homogeneous with respect to these conservation equations. So if I look at this one, this is like A and C I see in the support here. If I go along this network, each of these are going to have exactly, if I look at the set that belongs to A and C, right, this has 1A, this has 1C, 1C, 1A. So that all sort of matches. So this is giving me actually something that we like to think about as a homogeneous condition. All right, and so using those networks as our inspiration, we define sort of what it means to be partitionable, and then we give a mixed volume for these partitionable. So we're going to say that a space of conservation laws span by 0 and 1 vectors, okay, with disjoint support. So these are going to be your conservation laws. So you can think about these vectors, there's your coefficients and those conservation equations. And we have, the disjoint. I think we can really relax the disjoint, but it was sort of coming from this PDSC condition. And so that's what we had a little bit in our head. And then it's also partitionable if it sort of satisfies this homogeneous condition. So if I look at each of these monomials, if I sort of, dot product those exponent vectors with sort of the vector that I get from my conservation equations, they should all be the same. And so an example of something where condition 2 always satisfies. So if G is weakly connected, then the network will automatically satisfy condition 2. But condition 2 is not always satisfied. So that Edelstein network that we saw does not satisfy condition 2. All right. And so these are sort of nice, and what happens is, when I look at the mixed volume, I'm always going to get exactly one mixed cell, all right? So in this particular case, I can sort of see it coming across. So this is, I think my bottom rectangle there is for my 2 binomials. So binomials are nice because they're line segments. So when I take the Minkowski sum, right, I get, parallelotopes, right? And then I'm going to, depending on how many conservation equations I get, I'm going to have things that look like simplices that I'm taking the Minkowski sum. And so it's not surprising that our mixed volume is always going to be the, in this particular case, the volume of this parallelotope. But what is sort of interesting is I do only get one mixed cell in these cases. And so that's what this main theorem says. So for any partitionable binomial networks, any mixed subdivision has at most one mixed cell. And the volume can be computed accordingly. And so in this particular example of these species overlapping networks, this is where I want to pause because I think that this gives us a really interesting result here. So if I'm odd, I get a mixed volume of 1, right? And if I'm even, I get m over 2. And this is going to grow with m. Now, for all of these networks that I showed, all of these species overlapping networks, we actually know that they only have one solution. So the steady state, they all admit one real positive solution. So in half of these cases, in the odd cases specifically, right, my mixed volume is a good bound, right? And in the other half of the cases where M is even, my mixed volume is a very bad bound, right? So this is a very interesting family of examples. All right, so that brings me to my conclusion. So I sort of walked you guys through, what are chemical reaction networks? What are they used for? How do we go from our network to our polynomial system? Mixed volumes can bound the number of real positive solutions, and there exist families of examples where this bound is tight, and also families of examples where this bound is not tight. And so I have what Bern was keeping track. I have 2 minutes and almost 20 seconds. All right, and so I think the last thing that I wanted to say was share an anecdote about Frank, so happy birthday, Frank. All right, so I think in 2018, we were at the nonlinear algebra semester. And we were at lunch with a group of people, including a student. And over lunch, the topic came up, this graduate student that was starting to graduate, people asked her what she wanted to do in her future. And, she started talking, and then she was like, oh, I want to stay in academia. But like the sort of sentiment that you were getting was that, she didn't feel like she belonged in academia. And without hesitation, and with Frank's intensity, he looked her straight in the eye and said, you belong here, all right? And he said, I'm sorry if you don't, I'm sorry if anyone made you feel like you don't belong here, but you belong here. And so there's 2 things that I take away from that interaction. Number 1, I want to speak like Frank without hesitation. And and number 2, when Frank said that, and he said that, so, it was a little bit disarming, right? But it was so powerful to hear it in that disarming sense, right? But he was talking to the whole table. And I just really want to thank you, Frank, for cultivating a community where everyone feels like they belong. So happy birthday, Frank.
Thank you. Any questions?
I have a question about, thank you for the excellent talk also, and anecdote. I have a question about multi-stationarity, and it's possible you said this and I just missed it. So it's about counting the steady state solutions, and you want to detect because it matters in real life. So when you find the steady states, do you also check to see if they're stable, like if they're attracting fixed points?
Yeah, so it depends on the article that you're reading. So in some cases, they just mean multi-stationarity just to mean positive real steady states. In some cases, they mean non-degenerate, and in some cases, they mean stable. So it sort of depends on actually the paper that you're looking at. But they do really care about, what you really care about is stable. So.
Is there any extra algebra or combinatorics that happens when you have to check that?
Well, so stability is a condition on the Hessian. You want it to be positive definite, and so, right, so you do have some semi-algebraic conditions that are coming up. So.
Any other questions?
That might be a naive question. When you check, show that the bound is tight, you do it by finding that many solutions, or?
Oh, for this particular one, the species overlapping networks, there's 2 theorems that we're relying on. There's a deficiency 0 theorem and a deficiency 1 theorem that tells us that those networks have a single real positive solution.
Because the BKK theorem, there is a verifiable condition that you can check when the system is generic or not.
Yeah.
By looking at solutions at infinity. Do you use that? Or?
No, but I think that this is very interesting, and this came up a little bit in Matthew's talk, right?
It came up in your talk. So
yeah.
This condition that Maurice and then Tenran pointed out is
checking
the condition the Maurice Rojas and Tenran Chen that you mentioned. This is a translation of that.
Oh, okay.
It implies Bernstein generality.
No.
I,
But
I think also Jenya and Vanya also have a paper that essentially gives something to that as well.
Any other questions?
When you had the number n plus 1 times n plus 4 over 2, all minus 1, was there a special reason to separate the minus 1? Is that something coming from a construction or the geometry?
I think that sort of just came from when we were originally computing them and how we were thinking about the sequence. Like we had the number before we had the proof, right? And so
I see.
I'm not.
I noticed that also would be n plus 1 times n plus 2 over 2 plus n, which would be a binomial coefficient plus n, which is
Yeah, and I mean,
semi-natural?
we sort of actually had it written, like I was looking at my old slides, and I think I actually almost had it written in that way, and then eventually moved to the 2n plus 1 just because that's what appears in the literature. But that was exactly how we were thinking
Okay,
about it,
thanks.
yeah.
Any other questions?
So Barron made a convincing argument earlier this week that the best enumerative problems are those with degree 1.
All right.
Are those characterized in this setting?
Well, I mean, mixed volume 1 would be, right?
Well, there's the beautiful creation Feinberg theorem, which is an example.
Oh, yes.
And that's later generalized by
Yeah, there's some conditions that will, I mean, does it connect though through,
I'd say
like,
though-
could you make a connection between like some of the papers that people have done with like the maximum likelihood degree equal 1 to
Yes,
here?
actually, I made this, but it's in one of my papers with Rachel.
Oh, wait, so Frank and
So
Christian have a
yes?
paper that
We can-
say yes.
But I want to say, actually, in this case, Barrett is wrong, because if you only had one steady state, there'd be nothing like diurnal patterns. Every organism would exist doing one thing, the same thing all the time. And clearly, people, not just humans, but even simple organisms have different steady states they're in. So Barrett was wrong on that.
And Frank is brave enough to say that when he's not here.
I would say that if he was here. Yeah.
Well, it's recorded, so.
Oh, yeah.
Okay, great, thanks.
All right.